Hello everyone and welcome back. Alex here. Would you like to do some cool science at home? Most people are under the assumption that science is expensive and that you need lots of chemicals to do it, but that's just not true. The following video is one of my assignments from a science teaching course, asking us to make a science demonstration for one of our teachables based on the current science curricula. The purpose of this assignment was not only to create a fun demonstration using household products, but also to watch ourselves teach and to observe areas of strengths and areas that need improvement. This is the first video in a series of fun home science demonstration videos that span subjects such as physics, biology, chemistry, and general science. If you enjoy fun household science demonstrations and want to see more content like this in the future, please like and subscribe. With that said, enjoy the video.
Today I'm going to be presenting to you and demonstrating the properties of light using a microwave. And we're going to be doing this actually by doing something your parents have probably told you never to do before. And that's by sticking metal in the microwave. And we're going to be doing that in the form of light bulbs. So just before I start, I just want to preface a couple little things. Today I'm filming outside because I don't have a suitable place to do so inside. So I hope that's okay with you all. On top of it, whenever I ask a question, since this is being filmed and I don't have an interactive audience, I just want you to, I'm going to give you a few moments and just think about it, maybe take down a jot note and write down your expectations for what's happening. So yeah, with that said, let's begin. So today I have with me here 2 glasses of water, 3/4 filled. I also have 2 light bulbs, one of which is brand new out of the box, and one of them, this guy here, is burnt out, so the filament's broken. I also have with me a pair of heat-proof gloves, as sometimes handling the glass and the light bulbs coming out of the microwave, they can be a little hot. And then, obviously, a microwave. So, just starting off, what do you think is going to happen when I put a light bulb, a brand new light bulb, into a microwave? Alright, so let's see now what happens. So what's happening right now? And is it matching what you thought was going to happen? Perfect. So what did you see here? And why do you think that the light bulb lit up? So when I asked one of my friends that question, they responded and said that they thought it lit up because the microwave induced a current in the light bulb, causing it to light up. And that's actually a pretty great answer, but that's what we're going to look at here with this next experiment with a burnt out light bulb and the microwave. So what do you think is going to happen here? Perfect. So what's happening right now? Does it match what you were thinking was going to happen? Does it match your expectations? So, as we saw in both of these experiments, when the light bulb turned on and there was no rotation, there was a constant amount of light in both of them, whether the filament was broken or not. And this means that it's not actually the microwave inducing a current in the circuit, otherwise the light bulb wouldn't turn on with the burnt out bulb. So, in that case, why do you think the light bulb lit up? Perfect. So, if you answered that you think it's because the tungsten filament is absorbing energy or light from the microwave, you're correct. So, in this case, the light is actually coming in and being absorbed by the filament, which heats it up and then produces light. And in this case, here with the light particles coming in and being absorbed by the filament, would you think of them more as particles or something else? So in this case, it's actually perfect to think of them as particles that can interact and get absorbed by the filament. Interestingly enough, in this case with microwaves, they actually give off a low amount of electromagnetic radiation, meaning that the light and the energy coming from it is pretty low. Now, if you were to use larger energy sources, what would actually happen is the light particles, or energy particles called photons, would come in, strike the metal, and then eject an electron. And that's called the photoelectric effect, when you think of the light as particles. So now we're going to move on to the second part of this demonstration, with which what we're going to do is we are going to take this light bulb out, and we are going to put the rotating tray from the microwave inside. And we're going to allow the light bulb and the glass to rotate them as we heat them up. So in this case, what do you think will happen with the new light bulb going in and being allowed to rotate? Perfect. Just give me 1 second, and then we can start. Awesome. So what is happening right now, if you could just jot that down, and does that match your expectations? All right, so from that demonstration, we should have seen, and we did see, the light bulb flashing in and out, pulsing, where the light intensifies, and then it fades. So what do you think is happening in here? Do you think that light is still acting as a particle? So in this case, light actually isn't acting as a particle, and instead it's acting as a wave. So and this is a property of light and energy in which the this is actually a property of light and energy called wave-particle duality, where in some situations the light or energy can act as a wave, and in others it can act as a particle. So in that case, if it's acting as a wave, why is it intensifying and fading at different points in the microwave? All right, so if you remember from grade 11 physics, it's actually from wave interference, where you can have both constructive and destructive waves. In the case of constructive, the two waves are in phase and are added to each other and create a wave with a larger amplitude that's more intense, let's say. While in destructive interference, the two waves are out of phase and cancel each other out. So, just going off that, if constructive interference is occurring at a point in the microwave and there's a large amplitude and an antinode present, what do you think will happen with the light? Will it intensify or will it fade? And then for destructive interference, where the waves are out of phase, do you think the light bulb will intensify or fade? So if you answered that constructive interference is, when constructive interference occurs, the light will intensify, and when destructive interference occurs, the light will fade, you're correct. So great job. And I just want to finish this off with putting it into another sort of real world example for you that you would see every day. In the case of microwaving food, you know, and sometimes you microwave food and there's hot spots and cold spots. So in a microwave, wherever the wave microwaves are hitting a node or having destructive interference, no energy is being transferred to the food and it stays cold. While at points where there's constructive interference or an antinode, when that hits the food, a lot of energy is transferred and the food heats up quite a lot. Yeah, and that's it for my presentation today. Thank you all for coming. I truly enjoyed giving this presentation, and have a great day, everyone. Bye!